how do we quantify the impact of greenhouse effect on the radiative balance, and just simply by subtracting how much IR, infrared radiation, is radiated by the Earth, and compared to what's radiated at the surface of the atmosphere, at the top of the atmosphere. So that difference is what the greenhouse effect is trapping. So everybody, most of you got that correctly. There were some issues with this one. It's actually a very important one. And there were two answers. So part of the, I guess the low score here is that maybe people selected just one of the two. Okay? So let's go over this one. So the question was, it's a common counter-argument that people pose when the statement is made that human activities are causing global warming because of the CO2, right? So people say, well, but most of the greenhouse effects is due to water vapor, and CO2 is just a tiny amount of the atmosphere. Why? So the counter-argument to that is here, right? So CO2 is very important because absorbs infrared radiation where it's more intense, right? So it has a disproportionate impact to its concentration because it's very effective at trapping heat at the wavelength where the Earth emits at the most intense. The second one is incorrect because I put UV emission. So what's trapped by CO2 is not UV. It's actually transparent to UV. It's the infrared, which is the heat. I brought that infrared camera that you play with. So that's what's trapped. Right? The other one is correct, is that it has a longer lifespan than other greenhouse gases. It's carbon can be present as methane, CO2, carbon monoxide. There's different forms. It cycles through living things, so it has a longer residence time that affects the atmosphere than other gases. Okay. It is generated solely by fossil fuel burning. It's not correct. Volcanoes, a bunch of you and I produce CO2, so that's not correct. You're going to recognize that. Next one, I was actually surprised. We talked about albedo several times. Albedo is the reflectivity of the Earth. So the more white surface, for example, higher the albedo. So it cools the Earth. If you're really hot, if you're in the desert, you like to have light colored clothing because that reflects the light. So more albedo have a cooling effect, not a warming effect. Next one, already got that right. There's just understanding what the loops are. Negative loop, positive loop, feedback loops. Next one also is pretty good. What is the evidence of increased CO2? Explains current global warming. Really good. Volcanic eruption, have a cooling effect. Great. Okay, yeah. Now this one's a math one too. Okay, another math one. Okay. So let's do this one. Okay, so this one actually is true to what you did in the lab. Okay, so in the lab, if you recall, you had the ocular micrometer, which is a little rule in the eyepiece, and in all cases, it had 100 tick marks. Okay. And then when we measured it at 100x magnification, 100 times, we saw that it was exactly 1 millimeter long. So the 100 tick marks, it was 1 millimeter, which is the same as 1,000 micrometers. Okay. And then the conversion factor, or how much is each tick mark, was simply, okay, so 1 tick mark was 10 micrometers, right? So we all did that in the lab. And then the question was like, well, okay, we're going to measure something that's at higher magnification. Instead of 100x, we're going to change the magnification to 400 times. Right? So the first thing to recognize is that it increases the magnification by how much? How many times? 4. Okay. So it increases the magnification 4-fold, right? Okay. So the next thing to recognize is when we're magnifying, we're reducing the linear dimensions that we're observing. So if I'm looking at this page, and I'm looking at 1x magnification, I'm seeing the whole page. If I increase the magnification by 2, I'm seeing half of the page. If I'm increasing my magnification by 10, I'm seeing a tenth of the page. Does that make sense? Okay. You can imagine all of you use Google Maps, where you're zooming in. Is the same thing. You zoom, you increase the zoom, that magnification, you're looking at a smaller area. Right? So, as you increase the magnification by 4, the linear dimensions get reduced also by 4. So what happens to this conversion factor? If one tick mark is 10 micrometers at 100x, what is it at 400x? One tick is how many micrometers? 2.5, right? So we're dividing that by 4, 2.5 micrometers, right? So that's the conversion factor at 400x. And the organism that you measure at 400x was 10 tick marks. So 10 times 2.5 is 25. Okay? That's kind of the math exercise there. Great. Okay, the next one is, I asked this one in the last quiz. I have to double check. So maybe I didn't stress it enough. So here we go again. Brackish means low salinity. Full salinity, ocean water is like 30, fresh is 0. So brackish is like between 5 and 10, kind of in the lower part of the salinity spectrum. And we find that because it's very stressful there, diversity is low. There's not many species that can withstand those conditions of low salinity. Organisms prefer full salt water, so they're marine, or fresh water, they're freshwater organisms. So organisms that benefit from these conditions of low salinity are very few, but they're very productive. So the question is, what explains this? How come the few are very productive? And the answer is reduced competition, right? All those other things that I put in here, oh. I just read it. I think I put reduced competition twice. That's terrible. I wonder if I did that in the other one. Anyways, okay. All right. So these people got it right too. Okay, so actually then people did better than I expected. Right. Something, if you see something like that, you should tell me. I don't know. I guess I meant I put increased competition up here. Okay. So it'd be reduced competition, right? So if that's an interesting ecological phenomenon I wanted to underscore in this class, that it's not always where there's more food, but there's more resources where organisms can thrive because there's competition. That's another ecological factor that affects the patterns of species that you observe. And the last one, no problem with that one. In fact, that was also a repeat of, I think, another question I had in the previous quiz. Great. Excellent. So let's close this out. So went over the quiz. Okay, so what's next on the agenda? Okay. So because of the snow, unfortunately we didn't go to Nisqually. Well, actually got really nice in the afternoon that day. I don't know, not nice. But I think, there was an announcement on the campus. I think they posted it at 6. But I had an appointment like at 7, in a dental appointment, so I went there really early. And I was like sliding, and I was like, I need to get to school for my students, So I like sliding, and I get to campus. Nobody on campus. It's like, meh. Okay. And then it got really nice. Okay. But it's such a great trip to the Nisqually. How many of you have gone there? Actually, the majority have gone there. So those have gone there. What was the context? What was the class? Or what was the learning objective when you went there? Anybody want to share what they did when they went there?
After last week, I took some videos from the class.
Okay.
Posted on Discord.
Oh, you did? Okay, thank you. But you didn't go as part of another class. Okay, so people that have gone there for another class, why did you go there? Don't remember?
Not for a class.
Yeah.
Oh, so all of you have been there, but not for a class. Oh, okay. I was like, they didn't tell me why you went there. Okay, so this is what we're going to do. because there's a specific context that we wanted to go there. What I decided to do today, we'll do a little mini workshop associated with the field trip, for the context and the concept that I wanted to make sure were conveyed. Okay, so let me find my. I guess I didn't download it. I might download my lecture here. Oh, here it is. Okay, great. Okay, so there was a report I wanted you to complete, and I still have it as an assignment. But what we're going to do is we're doing a little workshop today. So I'm going to have you get together in small groups, maybe groups of 2, and we're going to answer all these things in this class, right? So if you take good notes, basically your report is done this morning, okay? But so my goal is that we contribute to the class to underline these important concepts, and then your job is simply to show me that you can explain it, you can articulate it in your own words, right? Okay. So there's 3 parts to the assignment. One is simply to explain why the wetlands are so productive, right? So I lecture about it. So I'd like you to discuss when I team you up in small groups. How would you answer that? Okay, and then we'll report out, and we'll have hopefully a comprehensive list of what's involved in answering this question. You know, why wetlands are so important on all these different levels. I have all this question, right? That there's different levels of the importance of wetlands. Why? The second one is another great thing that we learned by going to the Nisqually here. So it's a local wetland, and the history of its conservation, restoration, is very rich. And it provides all this information, all these insights on environmental studies, this combination of social and natural science. Specifically is understanding what motivated, besides the natural science reasons for preserving wetland, what are the political reasons, social reasons, cultural reasons? Okay? And what have we learned about what's an effective way to achieve such a complicated task, right? Considering so many pressures to deal with converting this wetland into water power or something else, right? The one that will help you with this today is the last one, because you can do that on your own. So that was another exercise to practice your research skills, which you've been using to do both your UN negotiations work and also your report. So I just simply want you to find one article on the science of marshes, and just do a little summary of it. Okay, great. Okay, so let's see how many people are clicked. There's 10 of you. Okay, so half of you are going to do what is the significance of wetlands, and the other half answer the question of the restoration. Okay, and then who was Billy Frank Jr.? That's a really important one. Okay, so there's 10 of you, so I'm going to do 2 groups of 3, 2 groups of 2, and then I want you to work for like, I don't know, let's say 5 to 10 minutes. Okay, so how about you 3 and you 2 work on number 1 on the first bullet point. Okay, and then how about you 3 back there, and then you 2 work on number 2. Okay, so I'll give you like 10 minutes. Okay, and then we should be able to come up with a really good list. Okay, okay. So I'm gonna. So 10 minutes is 20 till 11. Okay, so get together and discuss each of those bullets.
which group am I? I guess I'm in your group. Question 3.
Which takes us to the next one. Why?
What research is being done? So there, why are these systems? So,
Abundant supply of nutrients. I have the slides pulled up. Yeah, detritus. Disease. I think so. Yeah, it's basically like food, but not for us. It's for like bacteria.
Did you find it?
Lots of light and the water column and seafood.
of the refuge include the Migratory Bird Conservation Act, and Fish and Wildlife Act in 1956.
It's also probably.
So maybe we can Friday for this, negotiation with the company.
Okay.
Let's look.
So it's possible, or
I was gonna tell him today, but
Because of the Migratory Act.
Oh, is that the video?
Yeah.
Okay.
yeah, potentially it's just
Also, I feel like it looks more nice than like, I don't know, Cleanest Casino with the giant party lot there. That's just my opinion, that's not really. That's not that's not material.
well, sequestration.
Didn't you say it was a good place for like birds to reproduce?
Yes, it's like
He's not connected, so he's a big. You should watch it. I'll let you like. It's actually pretty funny. It's just. I think it's that it's his and there's like she retired. They make her dinner and she did a mistake. She and it's kind of.
what was it like ducks on the lid?
Yeah, that's like that. So. How's it going? Take care at all.
Hopefully, we're trapped all where we're supposed to be.
Last
We
week.
have, one more on.
How are you guys? How's it going?
Well,
Who's Billy Frank? Junior.
Native, grassroots activists.
Yeah.
Specifically focused on fishing.
Yeah, and it's all related to the bolt decision. I think John guys mentioned it. So I'll say as a little, tell us as much as you learned, but I'll add a few things. So yeah, they just added his name to the squalor just a couple years ago.
Yeah. Primary producers.
so recycling CO2.
So,
Did you find the partners?
the partners, no.
Oh, yeah. I think that's for like the ocean. Yeah. Kind of like an ocean.
Partners in restoration, lessons on effective collaboration to solve environmental problems.
It's operated by the U.S. Fish and Wildlife Service.
Yeah.
Um,
Oh, here it is. In partnership with the Nisqually tribe and Ducks Unlimited. They're the partners.
Who's this fish and shellfish? Ownership grants for fish and shellfish.
Does the carbon get trapped in the dome?
Alrighty, okay, so, that's exciting. Okay, you have this report, but you can do it collaboratively, okay? So, let's start with the first bullet point. So, the first thing is, let's understand wetlands, okay? So, the first thing is why, the statement was made in lecture as one of the most productive systems worldwide, including terrestrial systems. So, why? So those of you that love that question, okay, why are they so productive? I'll be like the board person here. Why so productive? So productive. Why? No answer.
Because where the two zones meet between the fresh and saltwater, there's it creates a food-rich environment.
What?
A food-rich environment and a place for keystone species to be where other things can't be.
Yeah, those statements are correct. But I guess I'm trying to look at the mechanism, right? So you mentioned those things. It's a mixing area. It's a rich environment, but that's more like the adjective. What's the mechanism? Well, why does a mixing lead to a rich environment? And what do we mean by rich? Maybe some.
The elevated, biomass.
But why? More productivity means more biomass. So we're still going to understand why.
Because of it being a tidal zone and the stratification that occurs, it creates a cycle that these species have been able to.
That's part of it, but I'll give you guys a clue. Let's define, right? When we're productive, there's more biomass, right? And the biomass, animals, plants, everything is really constrained by primary production, photosynthesis, basically, right? So plants, algae, things that make organic carbon are the base of the food chain. So the question is why are they so happy there? So if you're a photosynthetic organism, what makes you happy? Light. Okay, and? Nutrients. Oh, very good. Okay, so the first thing I'm getting at is lots, light, and nutrients, right? Okay. So let's start with this. Why there's more nutrients in this area than in other places? How come there's so many nutrients there?
From erosion from the rivers.
Great. Okay, so there's a lot of sources. One is the rivers bring a lot of nutrients because the rivers erode land, leach out the nutrients from the soil. It goes into the ocean, right? So what are other sources of nutrients? The rivers are the main one, but in that slide I showed you, there's a bunch of other ones.
The decomposition of
There's a lot of recycling there, right? So that's basically the outcome of the hyperactivity, right? So the recycling, there's a lot of decomposition that recycles nutrients. So one more. That's a really important one. I'll show you the slide. There's a slide that has all these answers. So hopefully you got it. Okay, so another source is upwelling, right? So we're in a coastal zone. So we get nutrients from the land, we get nutrients from the ocean, and then nutrients from recycling. Plants have to be really happy, right? Okay. Now, if you remember, one of the disadvantages of being close to the river is that it also brings a lot of sediment. And the sediment traps the light. So actually, this is not necessarily a lot of light, but just enough light for the nutrients to be utilized. But how do we get rid of the sediment in the coastal zone? If we have a lot of sediment in the water, the photosynthesis is really hard to conduct. Think about when we did the bud inlet study, we talked about all these processes by which sediments get removed. What were they? Flocculation. Okay, so flocculation gets rid of sediment. What's another one?
Increased mixing.
Yeah, less mixing, right? Great, excellent. Okay, so here we go. It's very productive. There's a lot of light and nutrients, and you can tell me why, right? Because, okay. Now, there's also ecological reasons. Now we explain why there's a lot of biomass. There's a lot of primary production, right? So there's a lot of things that use the light nutrients. So there's a lot of algae, there's phytoplankton, there's marsh plants, a lot of things. then they're used very efficiently. So remember how are these things used up? How they consumed? How they moved up the food chain? And in the coastal zone and the wetlands, there's 3 ways in which the prairie production gets eaten. Anybody remember? Huh. I feel like a failure as an instructor. I've been talking about this.
Animals that eat plant
Yeah.
material.
There's grazing, things eating living material. Okay, so let's call it. So there's grazers that eat the living, they'll be eating the phytoplankton, chomping on the seagrass. Okay, so what are the ways in which this gets moved up the food chain?
Becomes dead organic matter.
Dead organic, or dissolved organic matter. Dissolved organic matter, and then the other one is particularly organic matter, or we call it detritus. Okay? Good. Okay, so we answered the first question, right? There's lots of.
What's the difference between the dead organic matter and the detritus?
Okay, detritus. Okay, so well, dead organic matter is not a technical term.
Dissolved?
Yeah.
Dissolved.
Okay, so let's call it dissolved organic matter and detritus. Detritus is particles, piece chunks, and dissolved is. The chunks are so small that they don't sink. They just
Okay, so it's just like the size.
size exactly. So you have light material and dead material, and dead material comes in big chunks and little chunks. Don't write that in the exam. I say detritus and dissolved organic matter. Don't say little chunks, big chunks. Okay? Wrong. Okay, great. Hey, look at that. Isn't that cool? A lot of light, other nutrients, a lot of things. They're eating. Okay, so that answers number 1, right? I mean, why they're so productive? Okay, how do they support other ecosystems? Okay, so the Nisqually is this tiny area, but we still preserve it. So how does it support other systems besides the Nisqually?
It's mainly, it's one of the big uses is for migratory birds.
Okay, great. And I'll write this out. There's something called, in fact, it was popular when they found this out, called the outwelling hypothesis. Outwelling. It's like a well. So the outwelling is nutrients that are in this estuary are outwelled. They're exported. How are they exported? Well, there's migratory birds. A lot of people go to this to watch the birds. The salmon come in. So they use the salt marsh as habitat and nursery ground. As a feeding station. So it impacts systems outside the marsh. Okay, so but humans like it. Okay, so now about humans. Why do humans want what's so cool about the marsh? It's kind of stinky, it's dead chunks, dead little chunks. So why do humans like about the estuary? What are the services that it provides humans?
Because there's lots of food and calm waters for shipping areas, and then they're interesting. There's lots of stuff to see.
It is what?
They're interesting.
Sure. This is aesthetics, right? The aesthetics of the birds and stuff like that. Supports commercially important organisms, like shellfish, finfish.
Can be resources for like conservation knowledge and what was that another one? Not necessarily hunting, but like huntings and other things.
Sure. There's commercial, recreational harvesting,
Natural resources.
all this are biological. I would add the flood control and erosion control, right? So big storm events come in, and if you have marshes, they reduce the wave energy, and we know what happens when you reduce the wave energy. Sediment settles. As sediment settles, you can build more land, right? So you protect it, and you can build more land. Okay. Last question: wetlands and global carbon cycle. How does it relate to the carbon cycle?
It sequesters a lot of carbon because the detritus gets buried.
There's a lot of organic material. Not all gets eaten. Some is buried. or someone becomes trapped in the anoxic muds, which are, it is hard for organisms to fully decompose things when there's no oxygen. So there are areas of net carbon sequestration, right? Blue carbon, that's another technical term for it, right? So we love wetlands. We know a lot of them. We love them, okay? Excellent. So all of you can write a good little few paragraphs on the first bullet point, right? Okay, yeah, okay. All right. Let's talk about a little social science, okay? So, people that did the second bullet point. Okay, so what do you learn about the restoration? The film, we always watch the film. So I'll pose it this way, humans, like to exploit things. I mean, you've been reading about this in seminar books, like commodified nature. So Nisqually was a farm, and then it could be a great deep water port, it could be a great place of housing, be expensive real estate. But it didn't happen. It got protected. Now we're going to move I-5. We spent millions of dollars to modify I-5 to keep this well with sea level rise. So what do you learn about the social aspect?
The main thing was they used the Migratory Bird Act, or the Migratory Bird Conservation Act, and also the Fish and Wildlife Act of 1956.
Great.
And they had a lot of arguments for like erosion and migratory birds and the salmon, really the Chinook salmon, or the Nisqually tribe.
Excellent.
And also, it was I saw a note that it was a genetic pool for endangered and threatened species on the website.
Excellent. Endangered is correct. Okay. Okay, so let me highlight this. Great job. Okay, so we're shifting. Here's from a natural science perspective, right? We just need to understand how the system works. A little bit humans out of this picture here, right? But here is very human focused, right? So we want to conserve, but in back of your mind, to be aware that there's a human value associated with what state to restore to, right? So there's federal laws have been enacted to protect certain organisms. So migratory birds. So there's a federal, right? Is that federal? Migratory Act?
Yes.
And endangered and threatened species, right? So we understand the importance of them, so there's a federal protection for them. Hey, but this is super important, right? So culture, right? Salmon, the Nisqually tribe, the importance of culture. Some of you were to that lecture last week with of native ecology and all those thoughts about incorporating native knowledge. So that's huge, right? So there's all those motivations that are related to human interest in a sense. So that's what we're getting at, right? Hopefully when you did your research, you found this incredible partnership of groups that normally would be fighting and have differences of interest, right? So we have the feds. So the feds are like the Army, Navy, the Army Air Force Base, state fisheries, managing salmon, who gets a salmon, tribal, right? So tribal, there was a lot of fighting because of the tribes. When they ceded their territory, they were granted the right to fish and to harvest. And they were denied that historically until there was a bold decision. We won't go into a lot of detail on that, but the bold decision was kind of federal judge said no, now the state needs to make sure that tribes get 50% of the fish. Right? So that really has changed the whole landscape, the seascape of harvest as salmon, how salmon is managed and co-managed. Right? So there's federal, state, tribal. There's nonprofit, like Ducks Unlimited, people that want to hunt ducks forever, So all these groups had to work together, and also the central focus of their work is, salmon and birds, right? Salmon and birds. So you have to find a common ground to have all these groups work together. Right? So it's a really an interesting example of it, and there's all the things embedded in this story. So obviously, we had some time with deal with the Nisqually tribe, the Bold decision, and Billy Frank Jr. was part of the Nisqually tribe, and he was really instrumental in kind of fighting this injustice of not allowing the Nisqually tribe to harvest their salmon. So he actually went and sued the state, and then worked with Judge Bolt, and the Bolt decision, the judge, to realize this Bolt decision, which granted the Native Americans 50% of the fish. So now they named the Nisqually Wildlife Rescue after. So that was done a few years ago. Anything else about there? What else did you guys find anything interesting about the social aspect of the restoration? Okay, great. Okay, great. And how was she involved?
She advocated for preservation.
Okay, great. Okay. Good. You guys have something to write about for second bullet point? Right? Okay, great. Okay. And the third one should be easy, it should be kind of fun, right? Just look at it and catch your attention. That's science. Okay, great. So let me run through some of the answers here. These are from my slides from a lecture, I think it was last week, right? Or the week before. So here's the answers, like nutrients and light that you can bolded it, the physical, chemical factors, the different ways in which the organic matter gets moved up the food chain. I included this fact that even in areas that are supposedly stressful in the environment, in the wetlands, you have a lot of productivity because in those areas you have less competition. Right? So this is from lecture, and this is also from lecture. I think slides right to the other, right? So again, I went over some of the stuff that you were able to articulate, right? Okay, great. Okay, so let's move on. Last week, I started to build the case for anthropogenic global warming. Right? And I mentioned, I don't know how many, you probably encountered same situations, situation where, I was at dinner with relatives, and then one of my nephew, they said, I don't believe in this anthropogenic global warming, right? And it occurred to me, first of all, how difficult it is to talk about it. Well, for one, this is politically charged, of course, right? But even if you go in terms of discussing the evidence, which I try to gravitate towards, and I encourage you to do that, it's not really, as a scientist, we're trained to, what's the word? Some people say disinterested. That doesn't mean be apathetic. It means you're disinterested in the conclusion, you're interested in the evidence. So the role of scientists is to painfully demonstrate a certain conclusion and be detached from the consequence of that conclusion. It's hard to do. I mean, I think inherently people are biased, but that's kind of the goal of science is all this exercise, all this attempts to prevent that bias, right? So I approach it that way. I said, well, how do we know what we know? Like it's semantics. What is the evidence? So I hope I presented that to you in last lecture to say that when we determine to answer a question if humans are generating the observed warming, we start by saying that we first need to demonstrate that it's not due to natural causes. So how do we do that? Well, we examine all that is known about climate, what regulates climate, by natural sources. We look at all the variation that we've observed in the past in climate and explain it with those natural sources, right? So we will not conclude that humans are involved unless we can't find any evidence that all the natural processes that we understand cannot explain the change that we observe, right? That's one way. The other way is to then understand what is the human input for example, for greenhouse gases, and see if that contribution explains the observed warming. So hopefully what I showed you last week was how scientists build a case. It's not a single thing. It's not like in a dinner conversation. It's a silver bullet. Okay, here is a little one piece of information that destroys your argument, right? It's almost like a crime investigation. You'll see, crime movies, right? So there's a juror, and then there's a defense, and then a prosecutor. So you present a case. Who was the murderer? It was the butler or the ex-wife, or ex-husband or ex-spouse. So there's got to be there's got a motive. There's got to be, is there a smoking gun? So you should think about it that way. There's evidence that not a single piece supports the conclusions. That has to be a case, right? All the evidence needs to indicate, and there should be a shadow of the doubt of the conclusion, because that's kind of the analogy of how the scientific process should work. Okay, so I'm gonna show you a graph that provides evidence for anthropogenic global warming. Okay, and you're gonna tell me why. Okay, so I showed you this already, and I explained it. So and there's another little exercise for you guys to discuss. Okay, and it'd be an excellent exam question. Okay, so I showed you this before. Okay. So I showed these two images before. Hopefully you can see them from the back. And I'd like you to discuss, get into pairs, and you can think about it as an exam question. So the question would be, when you look at these two figures, how would they provide evidence that the current warming is not natural, but is due to anthropogenic causes? Okay? So maybe I'll just refresh your memory. This figure shows you increases in temperature here on this axis. So there's a cooling and warming. Zero is no change, and is due to different factors. Okay. This one shows you the dotted lines that are repeated 3 times here are actual data of observed temperature warming from 18-something to 1980 or something like that, right? So for a certain period of time, is all the observations of warming increase in the planet, and the solid lines indicate the predicted increase based on specific processes. Okay, so why don't you talk to your neighbor, come close to you, just 5 minutes, and then we'll report out. Okay, so 5 minutes.
CO2, volcanoes, and sun. Yeah.
Not the bar, but
Looking at the right-hand diagram, I just imagined it if we removed the CO2, and there would still be fluctuation, but I think the overall trend would be more flat. So I think that's evidence.
I just don't get this one. Maybe. What is that? And then combines anthropogenic.
To combat it.
I just don't even know this one.
And I feel like it would be more wavy with jumps due to volcanoes or burning, wildfires and others like that.
Mm-hmm.
But not marked very clear increases
And then 2 ones were natural forces and natural
mean the little whiskers, right? Little whiskers. The whiskers are the uncertainty. The uncertainty. It's like when you get an average and standard deviation, right? It's like you want to figure out the average height of this class. So we get everybody's height, you get an average, and the standard deviation is how the numbers, the average variation from the mean. So if you have a really wide whiskers, means that there's a lot of variation. Like this class, I don't know, I'm sure people don't know. So the average is, I don't know, 5'7" plus or minus 10 inches or something. Whereas everybody's the same height, it'd be 5'6" plus or minus 0. Like everybody's the same height. So it's what you call the uncertainty. The uncertainty or the variation. Some people call it error, but I don't like calling it error. Because error implies a mistake.
All of it is wrong.
Well,
Error.
Projected further in one direction than the other. So
it's not really a projection. It's a plus or minus.
Yeah.
It's a plus or minus. So again, the average height of an individual is 5'6" plus or minus 2 inches. Right, so it just reflects a variation. Okay, so maybe this time, why don't you tell me, great questions, but let's hear your report and then I'll go over the questions. So what do you think? The question is, let's start with this one on the left. How does this data provide evidence that humans are causing global warming?
I think the timeline, like the years.
No, we're looking at the left. This one. So this period, 1951 to 2010. Okay.
Because the observed readings don't correlate with the variation that was seen with natural levels before, so there must be another source contributing.
Great. So the quick answer to this is that the observed warming, this black bar is basically what's been measured. We measure this, and you can see the variation is small, the whiskers are small, and the reason for that is that there's like millions and millions of measurements of global temperatures during this period, and global temperatures are usually measured in the ocean, and there's all this averaging to make sure, because land heats up differently from water. But the fact that there's little whiskers is that the term is that average is well constrained. We have a lot of confidence in that number. There's not a lot of variation. Similarly with if you think of the height of the class, I know that height of the class is 5'6" at plus or minus 2. There's not much variation. Right? Okay. So it says, the green one is the amount of warming due to greenhouse gases. Okay. How come there's so much variation there? Because this is based on a calculation based on the physics of how we know CO2 and methane and other greenhouse gases, how much they affect the radiative balance. Remember, we did the radiative forcing, so it's all based on, we know CO2, the chemistry of CO2 is such that it absorbs so much infrared radiation, and based on the physics and chemistry and how much CO2 is in the atmosphere, this is how much temperature it should hold. Right? Does that kind of make sense? So this green bar is based on this calculation based on how much CO2 and methane and other stuff has been put in the atmosphere by humans, and using our knowledge of physics and chemistry of those compounds to generate an estimate of how much heating that they would cause. There's a lot of variation because we're dealing with all the different greenhouse gases. So each greenhouse gas has a different radiative effect. So the outcome is that there's a lot more variation in that number. Right? So that's just the whiskers are so big. Okay. Other anthropogenic forcings, there's a bunch of other ones, but this ones include most of the aerosols. Smog, pollution, soot, things like that are in the particles in the air. Those reflect light, and then they have a cooling effect. Right? So all this are the cooling effect, and the bar is huge, because again, there's all kinds of, the small, so there's a lot of variation, right? Now, then they combine them. So they combine those two, basically, let's say they subtracted this from that, and it reduces the variation. I don't know exactly why we reduce the variation. when they combine them, you reduce their variation. But the striking thing is when you compare the observed warming versus what you expect from the combined warming effect of greenhouse gases and cooling effect of pollution, it basically explains it. It explains it. That's what it said, right? This matches that, right? So what are the possibilities? Natural sources, right? Natural forcings basically include things like the cooling, the less or more radiation from space, from the sun, right? So every 11 years there's fluctuations in how much solar radiation reaches the Earth because of solar storms. Internal variability are things like El Nino, La Nina, decadal oscillations. So with all this period of time from this 60 years, it's basically balanced, is zero. When there's a La Nina, it's balanced by the La Nina. So basically this is a natural process balance of this 50-year period, and the imbalance can only be explained by this more greenhouse gases. Okay. How about this one? Anybody want to say something about this one? It's basically very simple. Want to give it a try? I'm gonna.
There's like a pretty clear upward trend over all of them. Like it's pretty clear that it goes up and it's not going back down, even with like variation and stuff.
Okay. There's we look at just the observed trend. So the dotted lines are repeated, right? So the observed trend, how we explain. So if we explain by saying, well, there's a constant increase over this period of time. We started here, so there's definitely an increase over time. But it's not that clean, right? There's ups and downs. There's a lot of noise. There's a lot of variation in the upward trend. Okay. And what they're trying to do here is say, well, we know what drives temperature is greenhouse gases. We know volcanic eruptions have an important cooling effect. We know La Nina, El Nino also have an input. Okay? So in here, what they're saying is, okay, if we just look at CO2 emissions, which is kind of like this one over time, if we just look at CO2 emissions and predict how much temperature would rise based on increasing CO2 emissions, we would see this, right? And it is a smooth line because you basically calculate how much CO2 is being burned, produced through fossil fuel burning. Why is there a little dip? I don't know. I mean, this as soon as it's based on in real data, they get maybe sometimes the economies are lower. There's a recession or something. There's not that much fossil fuel burning. It accelerates in the last part of this time period. So it doesn't predict all this noise, right? Well, if it's just CO2, if that's the only source of warming, it should be gradual, but it isn't. There's all this noise. Okay. So when the model includes their effect of volcanoes, which have a cooling effect, it doesn't explain the dips, right? So there's a dip here, there's a dip there, there's a dip there. So that matches volcanic eruptions. Right? So it's a little bit better fit. We take those two into account. And then when we take into account the 11-year cycles of variation in the solar constant, which maybe a misnomer because it's not a constant, the fit is even better, right? So the fit is best when we assume that there's three things affecting temperature: CO2, volcanoes, and the sun, which is what we know, right? Okay. So we consider them all. They kind of explain well the variation, but the important thing is that this net increase over time is really explained by increase in CO2. There's no more volcanoes or more sun. That's balanced over time. Right? Okay. So let's be skeptics, right? So as a scientist, you have to be a skeptic, right? So how would you critique this? You can say, well, sure, you tell me that this is evident, right? Because CO2, we know humans are imbalanced in the carbon cycle. There's a net CO2 increase. I still don't believe it. So, you need to have an example. You have to tell me why. Okay? So why? Why would this not be convincing?
Does spikes for all three of them, like going up and down are greater than what the predicted line would be. That makes sense?
Oh, this one?
The bottom one. How like when it goes high,
Okay,
it doesn't go as high as it
okay.
should, and how
So,
it goes
so you
low,
say
it
there's
goes
still
low.
some variation that's not explained yet?
Yeah.
Sure. So, but would that, would that indicate that it's not CO2, that's some other reason? Right, so that is that, you know, the argument would be, yeah, okay, let's try to find out, like, for this year, you know, why did it go more than you predicted, you know? So, that, I mean, that's what scientists do, is they'll keep tinkering and say, okay, our goal is to be able to, confidence that we have in the model, we can fully predict all the data, but like, you can hindcast and you can forecast, right? I think that's the way. Anyways, I'm going to move on a little bit, but I want you to think about it, because I hope I presented this not as a advocate. I'm saying, you know, you got to believe humans, but I'm showing you the evidence, and as a scientist, you have to critique the evidence, not the consequences of the conclusion, which is when you get into a debate, people are arguing about, well, this and that, or, you know. But, you know, we base it on evidence. So what is the evidence? Do we believe it? Maybe, I mean, I'll tell you what a counter-argument could be. Somebody could say, well, all these estimates are wrong. Or the science is not good enough, so I don't believe the numbers or something, right? I mean, that'd be, somebody could argue that. Counter-argument is, well, you know, do the science. Look at the papers and then tell me the method doesn't work. And it doesn't work. Okay, so I don't have that much. Well, I do have some time. But, if it's okay, I'm not going to give you a break. Okay? I'm just going to continue. Okay? There's a few things I'm going to make sure I cover. Because next week, we'll do more summary. And I'll go through through this again. I think it's important. And think about it. Okay? Think about it, because you're learning about this, and hopefully you can educate a little bit about it. Okay, so what I want to cover, there's some terms in your book that I have you read, so I'll tell you what they are and how to focus on it. There's a lot of technical stuff. Some of the chapters are pretty dense, and then towards the end is basically, so the chapters that I have you read, I think it's 9, 10, and 11, and I said 10 and 11, you can just look at the summaries in the back. They basically talk about the measurements of the impact of global warming as it's being measured. So I'll show you some selections of that. And the main point is kind of to understand that the consequences are well documented and they're consistent with this notion that human activities are causing global warming. And I want to mention a little bit about the Gaia, because the Gaia is so interesting, right? It's in your book. I don't know, do you guys talk about the Gaia in the seminar? So I'll tell you a little bit about it. Obviously, in the book is an example of saying, oh, scientists propose it, and then scientists don't do this. And I'll apply for a little bit, because the idea is that science is not, I mean, that's against putting some vitality in nature and stuff like that. So I guess I'll just give you some more insights on, from my point of view, more history of the Gaia hypothesis from a scientific point of view. Okay, so let's move. All right, so the first thing I'll do, this part, I think chapter 8 talked about this. It's a pretty good one, so I want to make sure these concepts get conveyed, okay? So I just went through some of the elements of the case for anthropogenic global warming. So scientists, another way in which they are addressing this global warming research question is to look at the past. The past should provide us clues about the present and the future. How? Well, the bigger question is not necessarily humans causing global climate change, but what causes climate change? What causes it? You know, and that's the fundamental question that we start with. You want to demonstrate that humans or some other factor are more important. We first need to understand how the system works, right? So a lot of research is just to understand how it works. And a big key to it is to look at the past. So it's called paleoarchives. Paleopast archives are stored information, and there's ways to get that information through chemistry and physics. Okay? So I'm going to tell you about it. Right? So what are my goals? Okay, so I'm going to tell you about what we understand about how climate change over geologic time. If you've taken in geology, you probably sound familiar to you. Okay, this Milankovitch cycles or is fundamental to understanding ice ages is long-term variation in climate, 100,000-year cycles in climate, right? And the question is, do we have any evidence over geologic time that greenhouse gases are implicated in climate? Right? So that relates to today. For, the classic, and that's still accepted, is that, climate over geologic temperature is driven by the sun. So now, today we're saying that CO2 is having an impact. Do we have any evidence for that over geologic time? Let's look, okay? Okay. So let's start with the data, right? So I won't go into details how this is determined. It's pretty complicated. It includes stable isotopes to determine temperatures over geologic time, millions of years. We have a knowledge of how temperatures varied over time. And there's been a lot of variation. So this is temperature over different time periods. Last million years, this is 800,000. This is, I think, present. This is the past. I think over 1 million years, 10,000 years, 2,000 years. Okay. So temperatures varied, right? So the question is, has varied of humans around? So how can this vary in the past, right? Okay. There's a strange white changes. So the consensus, if you go to any geology book, the answer is Milankovitch cycles. Okay, so what are Milankovitch? So Milan Milankovitch, the text got bigger. Milan Milankovitch was, I think, was a Serbian scientist. I don't know the history. History is always fascinating, history of science, but he came up with this idea that the climate of the planet over geologic time leading to the ice ages was explained by differences in the distance between the sun and the earth, and also the angle at which the earth is tilted towards the sun, which we know it now affects seasons. And he reasoned that, obviously distances, the farther the sun is from the earth, less solar radiation, so the earth is cooler. And if you have the tilt changing, you can have longer winters in the northern hemisphere. There's more land in the northern hemisphere, you get more ice caps, and that can lead to more and more cooling because of the albedo, the ice caps, leading to ice age. So he looked at data from the stars. It's just really interesting to look at how the Earth and the Sun have varied in terms of their position relative to each other. And he figured out that the distance between the Earth and the Sun and orientation varies in 3 cycles. Eccentricity. Eccentric means that you're not, if you're an eccentric person, you're kind of out of the ordinary, right? So eccentric means not circular. So the orbit of the sun the Earth around the sun is not symmetrical. So it's like an oval, and then the shape of that oval changes over time. We're over 100,000 year cycle. Every 100,000 years, it gets rounder or more elongated. And some important terms: aphelion means sun. Aphelion means far from the sun. Peri means close, when the sun and Earth are closest to each other. So that obviously, every 100,000 years, there's variations in how much radiation hits the Earth. There's another cycle. There's every 41,000 years of obliquity. In terms of obliquity, is a tilt. How tilted the Earth is relative to the sun, and that affects the length of the seasons. Right, the northern hemisphere is tilted away from the sun. Then that means the northern hemisphere winters are longer. Fascinating. Okay? Every 41,000 years. The last is a precession. The Earth actually has a wobble, like a top. It actually wobbles. And it wobbles every 23,000 years. How do they know this stuff?
We can look at certain types of rock and how the magnetic polarity is aligned to it. It is a fingerprint on it.
And another one you can set to here is also where the you can see where the North Star was, and there's something that is based on astronomical data. I think Most of it is astronomical data. Right. So Norman Lankovic says, well, let's put them all together. I'm going to create a model that looks at change over time when I add up all these different factors of how much solar radiation hits the Earth. And so it came out with this cycle. So precession, so this is how much solar radiation hits the Earth over time. There's a different periods, 20,000 years for precession, 41,000 for obliquity, eccentricity 100,000 years. And basically added them all together. So, for each year, given where you are in the stage of these 3 cycles, how much solar radiation hits specifically the northern hemisphere. Okay? The northern hemisphere is really important because, as I indicated, the length of the northern hemisphere winter is critical to long-term cooling or warming of the Earth because there's more land mass there. You can have more ice. The more ice, the more albedo, and it can progressively cool the Earth. Okay? And then he superimposed it on our data of when ice ages occur. And they kind of match, surprisingly, when there's glaciations, it matches when there is low net solar radiation. It kind of makes sense. Right? So that's kind of the consensus that over the period of time, the ice ages, this periodicity of ice ages and interglacial periods are due to molecular cycles. Now, so it goes to the question, well, if it's just solar radiation, does CO2 have anything to do with it? Well, that's an interesting question that relates to today, right? So, what was done is they looked at the temperature associated with the Earth based on just the orbits on it, basically the Milankovitch cycles. This is the predicted, the smooth lines. These hatch lines are actual measurements from ice cores, and your book talks about this. You can look at ice cores, and look at bubbles of ice cores, and get the bubbles out, and from the bubbles, you can determine the composition of the atmosphere and the temperature. So this is actual data, and this is the predictions of Milankovitch, and they kind of match, and surprisingly, in some places it doesn't match, but some peaks do line up. So the temperature lines up with what you expect from Milankovitch cycles in general. But the fit again is not very good, like when we looked at the models of sun and CO2 and volcanoes. So somebody said, well, we know the greenhouse is important, so why don't we look at the composition of greenhouse gases in the bubbles and see if CO2 could explain some of this variation. So the fit is better, right? So when you take into account molecular cycles and the amount of CO2 in the atmosphere, there's better fit, right? So again, this is another strategy in science is, we predict that certain things are important. So let's try it out to see if it does explain the variation. So in this case, it does. So CO2 seems to be implicated. So the conclusion is that CO2 is implicated or related to global climate change over geologic time. Okay. So this is an example. I don't know if this is from your book. Your book has something similar to this, but there's been important studies, mostly in Antarctica, or actually Greenland. Actually, the book talks about the Greenland one, where these cores have been taken over ice. So this is Lake Vostok in Antarctica. So this famous Vostok ice core. So they took ice core to get to the lake, but the ice core represents slice through time. So as snow falls and gets compressed, it traps bubbles. So you can have here a illustration of the core and how it gets compressed over time. So they got this core out, and there's a process to thawing it out, getting the air out of the ice, and determining concentrations of CO2 and other gases. And this is from your book. And this is a Greenland, so it shows the bubbles and the ice. They get the ice out in the cores. And this is again from your book. So Greenland and Antarctica, they're important places where this kind of research is done to look at the geologic type. Paleoclimate, ancient climate. Okay, so this is from the Vostok core. So what this shows you is data, and it shows you the middle bar is temperature, and on the top and the bottom are greenhouse gases, CO2 and methane. And why is it thick? The bars indicate the variation, because they're taking various samples and they get the average and the variation of it. So it just represents the uncertainty in that number. But as you can see, there seems to be correspondence, right? So the temperature, so the temperature peaks in here, and methane and CO2 also peak there. So there's some correspondence there. So the conclusion here is that the temperature co-varies, changes at the same time or in correspondence with the temperature. So here we're cautious, and you probably heard us talk about this idea of correlation versus causation. Anybody remember that? Okay. So in here you could argue they're correlated, right? So correlated means as one changes, the other changes. Does it prove causation? You always are cautious and say no. What would prove causation is more evidence. What would be more evidence? More evidence would be experimental evidence showing that there is a connection between more CO2 and temperature, which there is because of the physics of it, right? So you can do experiments, or you can have multiple lines of independent evidence showing the same result. So it gives you more confidence on causation. But you have to be very, very careful. So at this point, I would just say that this provides evidence that CO2 increase of greenhouse gases, co-vary with temperature, and because we do have a mechanistic connection between them, leading to a causal relationship, it provides evidence adding to that case, right? Because in the contemporary time, we do see that same connection and a stronger connection, more CO2 and more global warming, right? But this paleoclimate evidence also supports that. Okay, great. Here we go. I think it's just this is from your book, and this is from I think it's from Greenland. So the same data from Greenland. Again, different place in the world, one place in the world might have been different, so you have to do it in a bunch of different places. Okay, so this is from Greenland. So temperature here over time lasts 800,000 years, and CO2. So again, you see the way the peaks kind of line up. So more CO2. We still don't know, given this data, if CO2 precedes the temperature change or CO2 follows it. Okay? There's mechanisms to explain both. But the consensus is that CO2 helps to magnify or modify the amount of warming associated with the migratory cycles. So migratory cycles is true. The sun ultimately determines climate, but is amplified, the changes are amplified by greenhouse gases. Let's talk a little bit about the Gaia hypothesis. Okay, so I'm giving you a more mechanistic, maybe as a science would give you a mechanistic way that nature works, right? So the sun comes in, it creates all this stuff, right? And in your seminar book, we'll discuss this more in seminar, of course, seminar tomorrow's or last seminar. There's this notion that humans have not seen nature or scientists have not seen it as a in a vitalistic way, right? It's got its own history, it's got its own conscience, right? And there was a Gaia hypothesis that came up that kind of addressed that. So I'll tell you the story from my point of view of the Gaia hypothesis. Okay, so this is the question: does the Earth self-regulate? And is it for a purpose? Is there some consciousness, some vitality of this life force that leads to certain balance, right? And where did that come from? James Lovelock was a scientist, just passed away actually, not too long ago. And he worked for NASA, and his job was to develop a test to determine if life existed in Mars. Isn't that cool? So how would you are a scientist, and they ask you, hey, let's figure out if there's life in Mars. How would we know? Any ideas? Well, I mean, simplistically, you send a probe and see like this, there's plants or there's animals doing jumping jacks or something. So one is visual, right? But he said it was really hard, Mars is really far away. But so he had this interesting idea. He said, well, we know that there's life on Earth. So how do we know there's life on Earth? Well, there's green things and things jumping around, right? But he said, well, a clear example of evidence that there's life on Earth is oxygen in the atmosphere. And he said the atmosphere is biologically, 29% of the atmosphere is oxygen. So he said, well, we can see if there's life on Mars by just seeing if the conditions are favorable in Mars relative to the Earth, right? But then he started reflecting about the Earth itself and noticed that when you look at the climate on the planet, since life started dominating the planet, 4 billion years ago, even though there's some variations, there's some constancy. For example, in temperature. Temperature really hasn't varied as much as other planets would. If you look at Mars and Venus, you can predict their temperature very well based on their distance from the sun. But the Earth is kind of weird because the atmosphere regulates the climate. So his question is, how does this self-regulation occurs? Is life itself modifying the physical conditions for its own benefit to keep the range of oxygen temperature suitable for life to continue? And then Lynn Margulis was a scientist that was very interested in symbiosis and how organisms connect to each other to create more complicated communities. So the idea was like, well, can that be expanded to the whole planet? All those different communities work in concert to create conditions that control the abiotic climate for its own benefit, right? So that was kind of the idea, and it led to a lot of interesting research. Can we find mechanisms where there's self-regulation, and is it necessary to have a vitalism? There's that consciousness, a Mother Earth that's hidden somewhere. Thinking about this, or can we think about it as the word was a cybernetic system, like an oven? An oven's not alive, but you set a thermostat and it heats up and then cools, it heats up and maintains that temperature. Is it like that or not? So it led to that kind of questioning, in addition to the questioning that is in your book, right? Should we look at nature has its own agency, and is it a mistake not to think about it that way, not to give it, to just assume the agency by humans kind of dominating it? We can talk about it in seminar. Okay. So I will go through all this verbatim. You can look at it when I show you the slide. This all this summary of Lovelock and Margulis' ideas about the Gaia hypothesis. Okay, I'll skip that one. Okay. So what I'm going to finish is just summarize some of the things that your book talks about in terms of I think it's mostly chapter 9. And some of 10 and 11, so I just want to highlight some of the things here. So, what I want to show you is some of the data that shows the impact of anthropogenic global warming. I'll show you a lot of images, but this kind of summarizes what I selected in terms of the images. So let's go through these ones first. Okay. So, one of the things that we found is that the Earth is heating unevenly, and most of the impacts in the Arctic. I think some of you are doing a report on the Arctic, so kind of interesting to see what you can tell us more about the Arctic. The averages that we use to estimate these changes are averaged over space and time. So often, sometimes you see just a single average, but there's very geographic variation. Important to understand that the oceans have absorbed most of the increased heat. Right? And I think that goes back to the first lectures that we talked about the water has high heat capacity, and that's why high capacity, so it takes a long time to warm up the oceans. You also have circulation to the deep sea, so there's some time before the true heating is experienced in the atmosphere, so a lot of it is absorbed by the ocean. And we already see things change in atmospheric circulation, alters precipitation and drought patterns. I mean, it's interesting, I've given this lecture forever, but now you just look at the news, right? Like it's snowing in Los Angeles, and I have relatives in Canada, and they're in the 70s and 80s in Toronto, New York. Right? More water in the atmosphere, so you see increased flooding, increased hurricanes, so that's predicted by this increased warming, right? More water is in the presence of water vapor and circulation, there's disruption, right? So a lot of stuff that was predicted, I think we see evidence of it today. Okay. The book talks about this concern about this change is accelerating and creating what we call tipping point, and I'll explain what that tipping point in a minute. But a big concern is in the higher latitudes when the permafrost, areas are permanently frozen, thaw out, there become a release of carbon dioxide and methane and other greenhouse gases, so it would accelerate the change in temperature. Okay, so I can go back to this, you can see it in the slides, and I'll show you some pictures, mostly from your book. So this picture, shows you here the annual temperature relative to an average 1951 to 1980. So the average, if it's above the average, it's in red, below the average is in blue. So it's called an anomaly. So a lot of times temperature is shown as anomalies, differences from an agreed upon average. So you see an increase in temperature, it is uneven, right? So you can see some areas are uneven. And now you're understanding kind of the interaction of social and natural science and how different communities have different interests. You can see how this plays out, right? So there might be winners and losers in terms of at least a short-term low change, which affects their sense of urgency to act, right? The last one we talked about India, being particularly affected, and maybe their sense of urgency to act is more than another area that might be benefiting from global warming. This, again, with just more data, science is all about data. So this shows the averages of things like the number of cold days, cold nights, warm days, warm nights, taking into account that there's variation. So see the pattern is supported. So the number of cold nights and days are decreasing, and the number of warm days and nights are increasing. This one I thought was interesting. So I'd like to share with you. The bottom panel shows you the increase of temperature in the troposphere, which is the lower portion of the atmosphere. We've seen that before, I've shown you a lot, right? So this increase over time, and the peaks and valleys can be explained by El Nino phenomena. The valleys by major eruptions or La Nina phenomena, but there's a gradual increase of time supporting the contention that is more greenhouse gases, right? And consistent with that, in the upper atmosphere, we have shutter cooling in the stratosphere. Right? So the stratosphere cooling supports the idea that it's not the sun's increasing output during the 11-year cycle storms that's causing global warming, which is a major contention you see in the literature counter-arguments. If that was true, the stratosphere would be warming up, but it cools off. And the reason the stratosphere cools off is because two reasons. One is methane, which is a major component of the stratosphere, accounts for the warming of that area. The ozone absorbs UV light. And with less ozone, we're done a good job of not destroying more of it, but a lot of it was lost. So it's cooled the atmosphere because of that less ozone to trap the UV. And also, there's CO2 in that area, stratosphere, and the CO2 absorbs infrared radiation, but also irradiates it. And in the troposphere, because the infrared radiation is coming from the ground, the CO2 absorbs more than it can release. Whereas in the stratosphere, you're far away from the source of infrared, so it's actually losing more of the infrared than being warmed by it, so that leads to cooling. So again, this is what would you expect if the increasing temperatures was due to more CO2 as opposed to increased solar radiation. So you see, again, I want to highlight, in science you're looking at every possibility, and I'm trying to find data to support it or not support it. The whole point is that you have to build a case, it's not a single piece of evidence. Where most of the global warming is going, in the text I show you 90%, so I guess 93.4%. A lot of the global warming is to heat up at the oceans. Well, the different oceans, you can see this is the thermocline, so it's warming up. this one shows you that the surface is warming up faster than the thermocline area, which I think makes sense, right? So the surface is where there's mixing, comes in contact with the atmosphere. So the deep ocean is warming a little bit slower. This is more hurricanes. Can be explained by more greenhouse gases. This is a red line. This is potential intensity of hurricanes compared to a certain average. So the red, you can see, especially in the last part of close to the 2000s, the red increases. Aerosols is what you would predict, again, because of the cooling due to more aerosols, but actually we don't see that. So this is kind of historical data showing you, again, the correspondence between more greenhouse gases and increased storminess of hurricanes. And I think it's the last one. This is permafrost, just highlighting the concern of the permafrost thawing out. So permafrost leads to this idea of tipping points, right? So let's look at tipping points. Okay, so a tipping point, I found this nice illustration. Okay, a tipping point is a point of no return. A system cannot return to a stable state after perturbation and change to a different state, right? So this is a illustration of that. So here's a little ball, and it's in a stable state equilibrium. So there might be changes. It's going back and forth. It gets warmer, cooler, but it goes back to this equilibrium state. A tipping point is that it becomes so unstable that it falls into a different state. Right? It's hard to come back to the original state. Right? So that's a concern we have here in global climate change, that some of the systems that are being affected are resisting the change, and they go back. La Nina, El Nino, their things are cyclical in terms of the warming and cooling and how the Earth responds to this perturbation. I can relate to this Gaia hypothesis thing that the Earth itself has some manner of self-regulation. So the tipping point is where that changes. It changes to a different state. So that's our concern. Your book, why wasn't in your book? I think this is not your book. Let's take a look at this one. It has different areas that are considered tipping points, and this is you put this here from the back. So I'll kind of guide you through this, but please take a look at it when you review my lectures. Okay. So here's a picture of the planet, and it illustrates a tipping point. So there's three categories of tipping points. One, due to melting of the ice caps. If they melt more and more, there's less albedo, so less reflectivity, so increase the warming. Right. So it's one of those positive feedback loops. So it's color-coded, shows you where it's melting. Biome shift. Biome shift means that the biota is changing from a temperate rainforest to a tropical rainforest, something like that, right? And it shows you different areas where we're seeing this biome change. Amazon rainforest is a big problem, right? There's over harvesting there. So the Amazon rainforest is a fantastic way to regulate oxygen concentrations. Certain concentrations are regulated by the impact of the Amazon. When you reduce that, it can lead us to a tipping point. And the last category is circulation change. So circulation of the atmosphere and the oceans, which are determined as you go back to our original lecture when we talk about the atmosphere and the oceans, are regulated by differences in temperature, which drive the winds and drive density, which causes circulation. Right? So this is a tipping point that might occur if the system is perturbed. Oh, that's it. Great. That's from Great. Okay. So